Laura Kalbag. I know I have a very strange Kilkenny accent because I've come from Kilkenny today, but I am not originally from Kilkenny. I'll let you all guess where I'm from. Really hard accent to guess this one. So, I'm going to start off by telling you about the fact that I've been working in tech for around 15 years at this point. And I've worked in a whole variety of teams. I've worked as a developer, I've worked as a designer, I've worked running teams, I've worked for other people running teams. And one of my biggest pet peeves is this separation we create between all of our different concerns, between our areas of expertise. Sorry, my light's not bright enough on there. There we go. And realistically, there is so much overlap between what we do. So designers, when they're designing things, they are having to think up how things work, which really is making a lot of decisions for engineering. When engineers are implementing design, you're often having to fill in little gaps and make decisions based on little details. So you're kind of doing design as well. And project managers do the whole lot as well. But yet, we all just throw documents over the wall at each other so much of the time. We end up having requirements documentation and feedback documentation and not really talking to each other or working together or collaborating unless we're in a very rare, wonderful situation. And sure, there are better ways to communicate. There are processes we can engage. I mean, you can get qualifications in all kinds of communication processes nowadays. We can set our egos aside, even, if we wanted to. But sometimes we do just need some tools to help us work better together. And because this is a JavaScript event and we like to talk about engineering and development, I'm going to come at this from an engineering perspective. And we're going to talk about managing your application logic. So let's start off with some issues that we tend to find around software development and state management. First off, complexity. The bigger the app that we have, the more complex it is, the harder it is to manage. Even the smallest feature can introduce so much complexity in state. There's the data flow. Passing state between components can get really complicated and hard to follow, particularly if you're working with somebody else's code. And concurrency. So things that have to work at the same time. When different components are interacting with the same state simultaneously, we can really get ourselves into tricky situations. And testing and debugging. Because the more states you have, the much harder it is to isolate and reproduce those state-specific bugs. If you've used a lot of Booleans for your state, you'll know what I mean. And let's be honest, a lot of the time, all of the application logic and the sum of our application logic is essentially contained in one engineer's head. And that is a really tricky situation if that one engineer goes out of office for a day or quits altogether. And then you're stuck because you need to have this communicated in some way. So let's get started with some white noise. So this is my little mock-up that I did for a white noise machine app. This was based on an experience that I had when my dog was terrified of fireworks, and fortunately, you don't have fireworks here too often, but when you do, oh, he really hates it. So I got a white noise machine, such an amazing device. And so I decided to reproduce a version of this for myself. And so I started thinking about, well, what are the different states that I might have if I made a digital version of the white noise machine? Well, I got on-off state, I've got playing audio and pausing the audio. The on-off state is required, so you think about it in a physical device, on and off makes sense. On a digital, having it on a web app, you think, oh yeah, it'd be really great to have it just autoplay when you open up the browser. Of course, for obvious reasons, we can't have nice things in browsers. Autoplay requires a lot of different consents and things like that in order to make it work properly, because otherwise annoying websites would probably play ads at you the second you enter them. Other states we might have, well, different white noise sounds, because you might like a different sound. So I'm going to have white noise, I'm going to have waves, I'm going to have a fan state as well. And I thought, why not throw in some colored lights? Because colored lights are fun. And so I thought, well, yellow and green and blue. That way I can have soothing lighting while I'm listening to my soothing sounds. And volume up and volume down, because I want to have an additional control for that. Enter finite state machines. Now, who here studied computer science? So this is probably quite familiar to you. Who here actually uses state machines after studying computer science? Yeah, okay. Not as many, are there? So this is the classic example that you tend to see when people talk about state machines. And this is a coin-operated turnstile. And this here is a state machine. And so this is a model that can only be in one state at a time. This particular state machine can only be in locked or unlocked. And it can change from one state to another in response to an input. And in the case of state machines, your inputs are usually events. And the bits that are represented by the arrows are transitions. So you will transition from a state through an event back to another state. And so here, if we are locked, we could put a coin in and get it unlocked. But if it's locked and we just push, we just go back to being locked. And if we unlock it, put a coin in and push, we can unlock it. And there's a funny little icon here. Here, there we go. And this is called the initial state. So this is this little weird circle with an arrow pointing to one of the states. Very important. This is the initial state that our state machine will start at. So a key bit of information there, obscure little symbol. So here I'm going to get you to my version of a state machine that is for my white noise machine. So my initial state, I'm going to start with power off. And from there, I'm going to transition through an event that's toggle power to power on. And there we go. That is a basic little finite state machine. Next up, we want to add some actions. We want to have some functionality that is triggered by entering these states. So I'm going to add the actions here, and I'm going to implement my functionality later. So here on the power on state, I'm going to add an entry action. So when we enter the power on state, I'm going to trigger something called show buttons. And when we exit, I'm going to hide the buttons. Because I don't want all of the buttons for sound and volume and everything visible when I have power off. That wouldn't make any sense. I have to say I have to arrange my state machine nicely so you can read it. If you want to look at the machine that I'm building at any point, the final version of it, you can go to this sky.stately.ai/Laura. You'll get a bit of a clue into what's going to happen later if you check it now. Now I'm going to start with adding some state charts features. Who here's heard of state charts? Excellent. Well, I'm going to get to introduce the rest of you to the wonder that is state charts, because state machines are pretty simple, and there's a few things they can't handle. Whereas if you want to get to more complicated logic, state charts are your friend. And they are basically a visual extension to state machines that will help us model more complex logic. So one of the things that we can use state charts for is modeling hierarchy. So this is really helpful. So in my machine, I'm going to add some hierarchy in the form of inside my power on. This is now a parent state, and it's going to be a child state, where I'm going to have each state for the different sounds in my white noise machine. So I've got white noise state, I'm going to toggle the sound, I'm going to go to a wave state, I'm going to toggle the sound again, then I can go to my fan state. So you can imagine just pressing a button to toggle it through the different sounds. And then when that fan state is done, I'm going to toggle my sound back to my white noise state. So all of these states are able to be active while power is on, and that's how parent and child states work. And of course, each child state also needs its initial state. So you can see that little circle with the arrow to the initial state. So white noise is our initial state of the power on state. When we enter power on, we enter the white noise state. Next up, another great feature of state charts is parallel states. So this is the ability to have concurrency in our logic. So I'm going to make my sounds. I'm going to take all of those what I just added, and I'm going to put them in their own child state called sound. And now I'm going to get some nice layout going on again. I'm going to add a state for my lights. So that's the colors, and one for volume as well. So all of these states, sound and light and volume, are going to be able to happen at the same time, and that is because I'm going to make the parent state into a parallel state. So this is saying that when power is on, I can have sound and light and volume. Now I'm just going to quickly jump to this version, which I made earlier, because you don't have to sit and watch me add more child states and more actions. You know what that's about. But here now you can see I have this hierarchy going on. I can toggle my power on to go into the power on state. I have the entry actions, and I have actions on entry to all my states so that I can trigger the correct functionality for all of those states, with the exception of the volume one, which I haven't implemented yet. From here on, you'll probably hear me use the word state machine and state chart interchangeably, and that is because a state chart is a state machine, but a state machine isn't always a state chart. It's not particularly important, but I like to be accurate. Now I want to show you self-transitions. So this is an event or a transition which comes out of a state and returns back into the same state, and it's really useful for firing something off when you're going to return back to that same state. So this is very useful for updating something. So we're going to do this for the volume, and I'm going to add 2 self-transitions on my volume to do volume up and volume down. So I'm going to add a self-transition. I'm going to call it volume up. I'm going to put it up above because I like to have that semantic representation. I'm going to add a vol up action. And then I'm going to add another self-transition, and I'm going to call it volume down, and add an action, and that is going to be vol down. So that just enables me to hit those actions but return back to the volume state, which is concurrent with the other states. Next up, we have guards. Now this is a great way of adding conditional logic, because we don't want to be able to infinitely turn the volume up and down, because, I mean, for one, the Web Audio API doesn't support infinite volume, and so there's got to be a maximum, a minimum in there somewhere. So I'm going to add guards to each of my events here. So I'm going to guard the volume up with the condition if it is not the max volume. And I can implement the logic for that later on, implement the functionality for it. And for volume down, if it is not the minimum volume. And I'm going to add those into context, which is not something I'm going to discuss here today, but if anyone wants to have a chat about context later on, come find me at the party. So another concept that works really well with state charts is the actor model. And the actor model is essentially where everything in your system is an actor, and an actor can send and receive events, and it can change its behavior based on those events, and it's a really great way to make our logic a lot more modular and a lot more maintainable. It breaks it into actors that communicate with each other. So basically, when my state machine is running, it becomes an actor, and then if I want to communicate with other actors, I can do that. And so I'm going to create another actor, and I'm going to make an audio player that my white noise machine logic can communicate with, because it's quite useful to have that as a separate piece of logic. For example, if you wanted to decide to make your audio player compatible with MIDI, if you wanted to add a Bluetooth speaker functionality to it, it's useful to not have to be dealing with like your main machine when you're changing that logic. And so I'm going to fit to content so you can see what I'm doing. I'm hoping that text is big enough. Yeah, just about. And on my power on state, I'm going to invoke an actor that is called audio player. I'm going to also make sure I give it an ID of audio player. And so when I power on, I want to tell the audio player to play. So I'm going to add an action here, and this is a custom XState action, a built-in action called send_to, and this will send an event to audio player that is the event called play. And when I exit, when I power off, I want it to send an action to the audio player that tells that audio player to pause. Now, having a state chart that is also executable code means that you can do really cool things like simulating your machine, which is essentially giving you the means to walk through your machine as it will work live. So here the blue events are the available events for the current state. So right now I could go through toggling the light state, I could go through toggling the sound state, and I can do volume up and volume down as much as I like before I hit the conditionals there. And we can easily spot issues even just by walking through a machine like this. For example, when I do this, I realize I don't have toggle power to return to power off state. So that's a bit of an issue that I need to add to my model. So I can just go back into my model and add a toggle power event back. No, don't want a state done event. There you go, change it to standard event. I'm going to call it toggle power. And so now if I return to simulate mode, I can toggle my power on, I can toggle my power off, I can toggle my power on, I can toggle my power off. And that is how I walk through my machine. So through this demo, you might be thinking, wow, this is so easy to understand, and Laura doesn't even have to explain very much, and even Jim, the person who sits at the corner of the office, could maybe understand this. And this is because fundamentally diagrams are great, because we can all understand them. They're a visual representation of code, so there's a very low level of ability required to understand what's going on here. And that enables much clearer communication, and it's also much easier to collaborate when you're able to communicate with each other. And of course, it's easier to spot errors, which is really great for documentation too. And all of this helps with much better planning and organization. And so state charts provide all the benefits of diagrams, but as executable code. So this is like the key feature that is fantastic, is you can create that wonderful diagram, but it is also executable code. So this means your application logic can be visual and executable. You can have living documentation as well. Everybody understands it, which really makes it a logical source of truth. It is easy to keep up to date. So going back to the problems that we have in software development, we have the modular and hierarchical structures in state charts. That helps you handle complexity a lot better. We have much more explicitness and clarity, which makes the complexity much easier to understand. The visual representation is so useful for internal documentation. Like, imagine if you did a PR and you could see a representation of what your application logic is now in a little visual graph. It's so useful. And we can have a really clear structure for testing and debugging. So I've just added a description and some colors to my machine because that makes it more attractive when I share it with my team and they can see the things I want them to have their eye drawn to. And if I go to export this code, go to the little code tab, I can export it as JavaScript or TypeScript or JSON and some other things. I'm going to use XState version 5 beta, so I'm going to export this to XState. And if you look through, you can see that this is a representation of my state machine and it is just a JavaScript object. It's actually pretty easy to understand just as plain code itself. And if I scroll all the way to the end, you can see that this is where I can add my implementation details for the actions and the actors and the guards later on. Now I'm going to export that code to StackBlitz, where it will set me up with a little demo app where I can walk through my machine state. So I can just press these little buttons. It's a bit like the simulation mode. And there we go. This is a working demo just exported from that code. Now, if I jump to a version I made earlier, which looks a lot more like my little UI that I designed, I've got my little machine here, and here in the code, hopefully you can read it, you can see that I use this machine.provide method, and here I'm actually going to provide my implementations for my actions and for my actors and for my guards. I'm going to do this in a separate file from my machine. I'll do this in index.js file. Oh, there you go, it works. You can see I can go through all my soothing sounds. It's all working. That's volume up working. Yep, working, still working. Going up. Hopefully going back down now. Yep, there we go. There's the volume going back down. And how about lights? There we go, I've got a nice yellow. I can change the sound while yellow is on. Go through the waves, go to blue, go to green, and turn my machine off, and it's still green. So I clearly have an issue with my model. So, because I've got my logic separate from my implementation, I can return to my state machine very easily, and I can add another instance of the remove color action that I have on my light off state. So I'm going to take that, and I'm going to add that to the light state as an exit action. So whenever I exit light state, when I power off, it's going to remove the color. I'm also going to move the set volume that I've got on sound to the power on, because it makes sense to set the default volume when you power on. Something I noticed while I was making that demo. And now I'm just going to go to the code tab again and make sure I've got JavaScript, XState v5 beta, copy the code. And I'm just going to copy that across to my machine.js, keeping all of the functionality I had previously, just updating the machine itself. And ta-da! There we go. That way, when I turned it off, the green went away. It removed the color. Yep, go through sound. Light. Turn it off, yay. No more green. So do you always need a state machine? No. You'd think I'd say yes, but no. Especially if you have like simple and linear logic or very small and isolated components. Hey, if Booleans are working for you, Booleans are working for you, and you can roll with it. When do you need a state machine or a state chart? Well, the rest of the time, it's so valuable. If you have a complex system, if you want to make it easier to document and debug, when you want to be able to communicate your logic with anyone else on your team and have one shared source of truth for your application logic, it is incredibly valuable for that. And of course, when you want to create state charts, I would recommend XState. I'm sure if you have been involved in state management in any kind whatsoever, you're probably aware of XState. It's a JavaScript library that is framework-agnostic. You can use it with anything. There's also packages for React and for Vue and for Solid and for Svelte as well. And so that will help you run your state machines and your state charts. And from the creators of XState, there is also Stately, which is software for building and visualizing your logic as a team, and it is powered by XState, so it's fully compatible. So if you like the diagrams I did today, you're very much like Stately. I built them all inside of it. Thank you very much for having me, everyone. If you want to talk to me about state machines and state, or even privacy and accessibility, and other things that I really care about, come catch me at the party later. I am very friendly. I don't bite. Thank you for having me.